In this video, we will learn about stoichiometry and how to use stoichiometry to calculate values and quantities about chemical reactions. So we learned in chapter 10 that we had to balance equations by putting stoichiometric coefficients in front of the chemical formulas. Those stoichiometric coefficients tell us the proportions in which our chemicals react. That's similar to in a recipe when you're cooking. Those values in front of formulas tell you how much you need proportionately. So if you want your recipe to taste good, you have to mix things together in that right ratio. If you use 1 cup of salt, for instance, your chocolate chip cookies would not taste right. So you might own more than the required amount of salt. You most likely do own more than 1 teaspoon of salt, but you don't use all the salt at once. You use only like 1 teaspoon of it. So if you want to like double this recipe, you have to double everything. If you want to cut this recipe in half, you have to cut all the values in half. And you don't add everything you buy from the store. You will have leftovers and you'll put those back in the pantry, back in the fridge, wherever. Just follow those ratios. And so in chemical reactions, we follow those ratios. So when we look at those stoichiometric coefficients, we're going to be picking 2 different chemicals and comparing them, and so we can use those coefficients to relate 1 reactant to 1 product, 1 reactant to 1 other reactant, 1 product to 1 other product, 1 reactant, 1 product to 1 reactant. We're all just doing like comparing 2 things. Compare 1 product to 1 reactant or whatever. And so you can use this math here to scale recipes. It's just dimensional analysis. You can use it to calculate how much you need to buy, estimate costs, how much you can make out of what you own. It's useful. You can even use it to calculate costs. So in this chemical reaction, we'll be using this chemical reaction quite a bit. And so if we look at this chemical reaction and look at what's happening in the equation, you can see that there's a 2 coefficient in front of H2S. And so that means for every 2 H2S molecules, so that one is H2S, I will need 3 oxygens. And so this one is O2, oxygen's color-coded red, sulfur's color-coded blue. And so to figure out how many reactions can happen, I need to circle 3 oxygens and 2 H2S's. And so that is 1 reaction. And then I still have more, and so I can circle 3 more oxygens and 2 H2S's. And that's a second reaction that happens. And then on the product side, I can see that I had 2 reactions happening, and each reaction is going to produce 2 water molecules and 2 SO2 molecules. So we're going to have 2 of each product. And so I can circle, and these are the products of 1 reaction. And then I can circle the remaining waters, and that's the products of another reaction. In both of these pictures, I can tell that I have extra H2S, because these coefficients just tell us the proportions. And so we can use these coefficients to make proportions. And so we could say for every 3 moles of O2, I need 2 moles of H2S. I could say for every 3 moles of O2, I'm going to be making 2 moles of SO2. We're just going to grab those numbers out in front and put the word mole right after the number. 2 mole of SO2, I will make 2 moles of H2O. So we can use those mole relationships as conversion factors in math. And so it says how many moles of H2S is needed to react with 5.24 moles of O2. And so I can start with my 5.24 moles of O2. I need to cancel out my moles of O2, and I need to find moles of H2S. And so I need to find my coefficient for O2, which is a 3, and I need to find my coefficient for H2S, which is a 2. And so then I can use my calculator to calculate that value. 5.24 times 2 divided by 3. And that is 3.4933 moles. And then I have 1, 2, 3 sig figs, 1, 2, 3 sig figs. So that is 3.49 moles. These mole amounts in the middle are exact values because we can count them. And so counted things are exact values. So they won't influence your significant figures. So we're just using those coefficients in our math. So if we go down to the next question, it says how many moles of SO2 can form from 5.24 moles of O2. 5.24 moles of O2. I need to cancel out my moles of O2, and I need to make moles of SO2. And so there's a 3 coefficient in front of the O2, and there's a 2 coefficient in front of the SO2. This also works out to 3.4933 moles because the numbers are exactly the same as in the previous problem. And so that will be 3.49 moles. Here's a practice problem for you. Go ahead and pause the video and try to work it out on your own. It reads how many moles of H2O formed if 3 moles of SO2 formed. Okay, let's go over this. So we're trying to find moles of H2O, and we're given 3 moles of SO2. So we have to start with our 3.00 moles of SO2. We have to cancel out our moles of SO2, and we have to find moles of H2O. So I need to look at the coefficients. SO2 is here. That has a 2 coefficient. H2O is here. So that also has a 2 coefficient. And so this works out to 3.00 moles of H2O. It's a good idea to list your compound so that you remember which compound you're talking about moles of. They're like apples and oranges. You have to know what you're talking about, because if you want to cancel out apples and find oranges, you have to make sure that you're canceling out the right substance. So 3.0 moles of H2O. Well, so far this semester, we have learned many pathways to moles. And so now it's time to pull all those different mole methods together so that we can wrap what we just learned with things that we've learned before. So you have many different pathways to get to moles from whatever starting unit you are currently at. So this is the one new conversion factor for chapter 11. All these other ones you have seen before. And so if you're given a mass, which is commonly in like grams or kilograms or something, then you're going to be using molar mass as your conversion factor to get to moles. If you're given counts of things, like how many atoms of something you have or how many molecules you have, then it's Avogadro's number. Both of those were covered in chapter 5. You can also be starting with a volume. So if you're starting with a volume like liters or milliliters, then you can use the molarity in order to get into moles, because molarity has units of moles per liter. Molar mass has units of grams per mole. We also learned about, for gases, you can use the ideal gas law, where N was equal to PV over RT. Now, we also learned about density and mass percent composition. And so both of those were for pure substances. And so both of those can lead you to mass. You could also, if you had the density of a solution, then you can use that density of solution to go from a mass of solution to a volume of solution. Densities have units of like grams per milliliter. So you just have to know what it's density of. If it's density of a solution, that's going to take you to mass of a substance. If it's density of a solution, it's going to take you to volume of that solution. Okay, so we're mostly going to be sticking in that column though, not really focusing on things over here. We're going to be focusing on identifying, do we need to use molar mass? Do we need to use molarity? Do we need to use Avogadro's number in order to get to moles? Then, after we find moles of one substance, we can use the coefficients from the equation to switch into moles of a different substance. And then you can, of course, get out of moles. And you can get out of moles in the same way that you have on this side of the diagram, into whatever end unit you need. So here's an example of a mass-to-mass conversion. So when in doubt of what to do, go to moles. So if you're given a mass of something first, you're going to use molar mass to find moles of that substance. Use the ratio from the balanced chemical equation to find moles. And then use the molar mass of the other substance to switch into mass of the other substance. Here's an example of that process. It reads, how many grams of SO2 will form if 56.20 grams of H2S completely react according to the reaction below? So we are trying to find grams of SO2, and that's given this many grams. So we are starting here with 56.20 grams, and we're trying to go to the mass here. You can see I've given you molar masses of those compounds. That's to save time. So we are given 56.20 grams of H2S. We need to cancel out grams of H2S, and we need to get into moles of H2S. This is going to be my molar mass as a conversion factor. So the 34.08 is attached to the G, and the 1 is attached up there. Now I need to cross out my moles of H2S, and I need to obtain my moles of the other substance. So my other substance was moles of SO2. The coefficient for H2S is a 2. The coefficient for SO2 is also a 2. And then, so these are the coefficients. And then I need to cancel out my moles of SO2, and I need to get into grams of SO2. And so this is my molar mass. Again, it's just the molar mass of the other substance. So again, the numerical value is attached to the G, and that's per 1 mole. So if we plug that all into the calculator, we get 105.655. And then we look at the units. That grams cancels with that grams. Moles cancels with moles. Moles SO2 cancels with moles SO2. I am left with grams of SO2. Now for sig figs, I am given 4 sig figs. So let's round to 4 sig figs. And so that will be 105.7 grams of SO2. Here's a practice problem for you. Go ahead and pause the video and try to work it out for yourself. It reads, how many grams of O2 are needed to consume 56.20 grams of H2S according to the reaction? All right, are you ready to check your answer? Let's go. This is what we're trying to find, and we are given this amount. So remember, we're going to go from grams of H2S to moles of H2S. Then we're going to switch into moles of the other compound, and then into grams of the other compound. And so let's do that. We have 56.20 grams of H2S. We need to cancel out grams of H2S, and we need to find, that will give us moles of H2S. This is my molar mass, and so I can go ahead and plug in the values. Remember that molar mass always has like a 1. So you can think of it as grams per 1 mole. All right, and then here we need to switch from to our other compound. And so we need to go from H2S to the other compound, which is O2. We need to, so these are our coefficients. And this was our molar mass. And so then we need to use the molar mass again, because we are asked to find a mass. And so molar mass is out of per 1 mole. And then the coefficient here is a 2, and that's a 3 next to the O2. So let's go ahead and type that into our calculator. 56.20 times 1 divided by 34.08 times 3 divided by 2 times 32.00. That is 79.1549 grams. I'm given 1, 2, 3, 4 sig figs. So I need 1, 2, 3, 4 sig figs. Did I type something in wrong? Let's find out. Nope, I was right. The answer was none of the above. So that should have rounded to 79.15 grams. Here's another practice problem. It reads, how many liters of a 0.115 molar potassium iodine solution is needed to react with 0.104 liters of a 0.225 molar lead nitrate solution? And then the balanced chemical equation is given below. Pause the video to try to work that out. Okay, let's go over this. Now remember that every time we see a molarity in a problem, that is going to be used as a conversion factor. So that's the conversion factors that are going to help us find our moles and get out of moles. And so when we turn that into a conversion factor, it looks like 0.225 moles per 1 liter. And this is 0.115 moles per 1 liter. So let's go ahead and get started. We always want to pick something with a simple unit as our given starting value, and we're asked to find liters. So we are starting with liters and we're trying to end with liters. So since we're given liters to start with, I'm going to write, and then that was of the lead nitrate solution. So I'm going to label that before I forget what solution I was working with. And then I need to cancel out my liters and I need to get to moles. This is my molarity. Always just look at the units to make sure that you're lining up your units right to cancel out. And so the 0.225 was attached to the moles and the 1 was attached to the liters. And this is still of my lead nitrate. If you like, you can label that with solution. Now I'm in the compound, moles of the compound, and so I can cancel out my lead nitrate. And I would need to get into my moles of potassium iodine. There's a 2 coefficient in front of that, and then that's a 1 coefficient. Remember, 1 coefficients are not written. Now I need to cancel out my moles of potassium iodine so that those cancel out, and then I'll be left with my liters of potassium iodine solution. And that's my molarity again, only now it's my molarity of the other compound. And so we have 0.115 moles of potassium iodine solution per 1 liter. Let's go ahead and type that into the calculator. 104 times 0.225 divided by 1 times 2 divided by 1 times 1 divided by 0.115. And so this works out to 0.40695 liters. And then for sig figs, everything has 3 sig figs. And so I need 1, 2, 3 sig figs. And so that's going to be 0.407 liters. Good. All right. Let's figure out this one. This one says, what is the mass of iron that will react with 5.50 liters of O2 at STP? And so we have to remember that STP applies to gases. And go ahead and pause the video and try to work this out. Okay, let's work this out. So STP is related to gases. STP is standard temperature and pressure. The standard temperature is 0 degrees Celsius, which is 273.15 Kelvin, and my pressure is 1 atmosphere. I could also remember what I get if what volume 1 mole of gas at STP occupies. And so if you look back in your notes from the previous chapter, you should find that at STP, 1 mole of any gas occupies 22.4 liters of volume. And so I can use this as a shortcut in my math. If you do not remember this shortcut, you're also welcome to use the ideal gas law to find how many moles of O2 you have from this volume. So you're given a volume of gas. See, it is a gas. And then we need to find a mass of a solid. And so we're going to be ending with iron. So we're given 5, trying to find mass. I should have written find. Okay, we're trying to start with our liters of O2 gas. And then since we are at STP, I can cancel out my liters of O2 and I can get straight into moles of O2. And then so 1 mole of any gas occupies 22.4 liters of volume. Now I can cancel out my moles of O2 and I can get into moles of iron. And so that will be a 3 coefficient and a 4 coefficient. And now it's asking me to find a mass of iron. So I can cancel out my moles of iron and I can find my grams of iron. And if I look on my reference sheet, my periodic table, my molar mass of iron is 55.85 grams. Let's type that into the calculator. 5.50 divided by 22.4 times 4 divided by 3 times 55.85. And so that is 18.284 grams of iron. Now sig figs, I am given 3 significant figures, so I need to round this to 18.3 grams of iron. You just look at the 8 and figure that you need to round it. All right. You can also use those stoichiometric coefficients in order to predict proportions. of things in a more conceptual manner. And so this problem reads N2H4, so that's dinitrogen tetrahydride, decomposes at a fixed temperature in a closed container to form N2 gas and H2 gas. If the reaction goes to completion, the final pressure will be blank. And so let's go ahead and write out that reaction. And so that's a gas, and it decomposes to N2 gas and H2 gas. And so now I need to figure out my coefficients to make sure that I'm balanced. 2 nitrogens on the reactant side, 2 nitrogens on the product side, 4 hydrogens on the reactant side. So I need to have 4 there. So on the reactant side, I have 1 mole of gas. Let me rewrite that. It looks like a Z. So 1 mole of gas on reactant side. And then I have 3 moles of gas on my product side. So since the number of moles is tripling, my pressure will go up 3 times the amount. 3 times the number of moles, 3 times the pressure. The number pressure, if we look at our equation, PV is equal to nRT. So if we increase the pressure, if we increase the number of moles, then my pressure goes up. So if we increase the number of moles, then my pressure is going to go up. So they are directly proportional. And you can also work it out mathematically if you want to. Here's a practice problem for you to try to work out on your own. It reads, in the electrolysis of a sample of water, 100 milliliters of O2 was collected. What volume of H2 was collected? Go ahead and pause the video and try to work it out on your own. Okay, you got an answer? And so we are told that we have 100 milliliters of O2, and it's asking us about volume of H2. And so since that's a 1 coefficient and that's a 2 coefficient, we're going to have twice the volume. Again, if we look at our ideal gas law of PV is equal to nRT, then as we increase the N, we're going to increase the volume. And if you look at the 2 containers, this is a setup for the electrolysis of water, you can tell that one of the test tubes has a higher volume of gas inside. And so now we know that must be the H2 side, and the other side must be the O2 side. All right, if you want a cumulative practice problem, this is a good one. This will take into many different concepts that we've learned about so far in this course. It reads, determine the identity of an unknown metal if 1 gram of the metal reacts with excess acid to produce 351 milliliters of gas at 25 degrees Celsius in 1 atmosphere. We are told the ideal gas law, we are told an R value, and then we are told an equation, a generic equation, but we don't know what metal it is. So how can we possibly identify what metal it is? Pause the video and try to think about what we could use to identify the metal. Okay, we could identify the metal by finding the molar mass of metal and compare to the periodic table. But how are we going to find molar mass? Well, molar mass has units of grams per mole. We are told grams, and so we could find moles. And so we are given grams, and so we would need to find moles of metal. How are we going to find moles of metal? Well, we are given enough information to find moles of H2 gas, and so from that we can figure out our moles of metal. And so in this equation, we can work out our moles of H2 gas. According to my ideal gas law, PV is equal to nRT. My pressure is 1 atmosphere. That N has too many. My volume, let me do algebra. PV over RT is going to be equal to my N. So my PV, my volume has to be in liters. So that's going to be 0.351 liters. My R value is 0.08206 in this problem. You can use 0.58 if you want to, per mole Kelvin. And my temperature has to be in Kelvin, and so we got to convert to Kelvin. So 25 plus 273.15 is 298.15 Kelvin. So that's 298.15 Kelvin. So we have 1.00 times 0.351 divided by 0.08206 times 298.15. And so that is equal to, so my moles of hydrogen gas, I don't want to forget that's hydrogen gas, not my metal, is 0.14346 moles of H2, keeping extra sig figs for now. And then I will need to cancel out my moles of H2 and get into my moles of metal. And so there's a 1 coefficient in front of my metal, 1 coefficient there, and so that is equal to my moles of metal. So my molar mass is equal to my mass in grams given to me in the problem and my number of moles. As long as we get our units to match what we're searching for, then our setup is good. And so this will give us molar mass. 1.00 divided by my previous number of moles. And so that tells me my molar mass is 69.70 grams per mole. And so let's compare that to the periodic table. And then gallium has a molar mass on my yellow sheet of 69.72 grams per mole. So I'm going to say it's gallium. Yep. All right, watch the next video to learn about limiting reactants.